All right, today we're going to be talking about integration by substitution, which is kind of a hefty topic. And there's a few different ways of kind of understanding this topic. So I'm going to show a couple different methods to you. I'm going to kind of stick with one method for most of the lecture, and then at the end, I'm going to point to a different thing called pattern recognition that some students find easier. So in section 5.1, we learned how to integrate these basic functions that you could essentially break apart so that you would have something like single terms raised to powers. So like here we have 4x squared. So we have a single term here raised to a power. And so to do something like this, if you recall, we add 1 to the exponent, so it becomes 4x cubed, and then we divide by that new exponent. And then we say plus c. Sometimes it was a little trickier. If we had something like this, we would split it apart. Remember, single on the bottom means to split, and then to simplify, separate, simplify, and then integrate. So here I want to simplify this. So this would be x squared. So 2 minus 5 makes it 4x to the negative 3. This one I'm actually going to write as 1 over x because that is special. That one is natural log. So if we add 1 here, we get 4x to the add 1 makes this negative 2, divide by that new exponent, and then this would then be the natural log of x plus c. You could simplify that to be negative 2x to the negative 2 plus the natural log of x plus c. If you ever forget that 1 over x is ln, hopefully we'll remember if you try to write this as x to the negative 1 and add 1, you get 0. And you cannot divide by 0. And so hopefully that will help you remember, oh no, I'm doing something wrong. So that is the special circumstance of ln of x. But today we're going to be talking about things like this. Which we did talk about how we could integrate this by multiplying this all out and then integrating it from there. But there's a way where you don't have to do that. And in some cases, you cannot do that, or it would take forever and be incredibly tedious to do something like that, like here, to the 7th power. There's no way you want to distribute something out, multiply it over and over and over again, or use Pascal's triangle. That would be really tedious. So instead, we do something called U substitution. And what we do in U substitution is we're essentially changing the variables. Instead of x, we're making a substitution and introducing a new variable called u. So we say, what if instead of using 4x minus 1, we just called this whole thing, the whole thing in the parentheses, which is often what u is, we just called that whole thing u. Well, consequently, if I write down what u is, you always need to write down the derivative of u. The derivative of 4 would be 4, and the derivative of x, dx. Okay? So now we're going to substitute. Technically, we're substituting in for this and also dx. So my recommendation is to solve for dx. Here we get du over 4. So if I go to rewrite this integral, I have this 4 right here. I have this guy, which now we're calling u. So u, and he's raised to the 7th. And then instead of writing dx, I'm going to write what we just saw for. Dx is du over 4. So I'm going to substitute du over 4. Now notice here that the 4's simply cancel out. So I have, really, it's just u to the 7th du. Now some people, I had different calculus professors explain it a few different ways. So I had calculus in high school, and then I took it again in college. And then gone to countless different seminars and trainings in the last couple decades, and different ways of teaching this. One of them is to solve for dx, like I explained. The other one is to just recognize that this is du. Like to move the 4 over here and realize, oh, 4 dx is du. Basically the same idea. I think always solving for dx keeps it really consistent. And so every time if you solve for dx and substitute and then simplify, you should be good. So here I'm going to have u to the 7th. Now I'm going to integrate, which integrate means I'm going to drop this integrating symbol. I'm going to add 1. So it becomes u to the 8th divided by 8 plus c. And then you resubstitute, like I plug back in. What is u? U is 4x minus 1 to the 8th over 8 plus c. we can check it out and see, does it work? If I take the derivative of this, do I get this? And you would, because the 8 pulls down, so you get 8 over 8. 4x minus 1 to the 7th multiplied by the derivative of the inside, which is 4. And so this is what we get, and it matches. Okay, so this is talking about how we can do that. This is talking about guidelines for choosing u. If it's inside the natural log, like the argument, you choose that to be u. If it's raised to a power, like the one we just did. If it's an expression that an exponential function is raised to, so that's like e to the 2x. So if it's something with an e, something like this, you're going to make this the u, an argument of a trig function. So like sine of 5x. This is the argument of the trig function. So these things inside the natural log, if it's an expression raised to a power, so this would be your u, exponential function, that would be your u, and inside the sine, cosine, tangent, etc., that would be your u. So let's practice doing a few of these. So I see I have 6x squared on the outside, and on the inside I have 2x cubed plus 5 to the 4th. Now we're going to pick the thing to be the u that is inside the parentheses, this thing that's raised to a power. So I'm going to write down what u is. U is 2x cubed plus 5. And kind of another way to think about it is it's the one where if you take the derivative of it, it's close to the other thing that's sitting there. What I mean by that is notice this is raised to the 3rd power. When I take the derivative of something to the 3rd power, it would go down 1 and become to the 2nd power. So it makes more sense to choose this as my u, because remember you're trying to substitute in for du as well. Du in this case is going to be 6x squared dx. Then we solve for dx. So if I rewrite this, I have that 6x squared there, or you can just recognize, oh, that's du, and just go ahead and take that away. And then you have your u to the 4th, and then dx is du divided by 6x squared. And these simplify perfectly. So you're just integrating u to the 4th du. So the antiderivative will be u to the 5th over 5 plus c. And then you put back in what u is, so 2x cubed plus 5 to the 5th over 5 plus c. Let's try this one. We're going to pick the thing inside the square root. So 4 minus 2x. The derivative of that is negative 2 dx. Solve for dx. So now I'm going to substitute in this for dx and this for u. So negative 2 square root of u du divided by negative 2. The negative 2's cancel. I can rewrite u to the square root as u to the 1/2. And when you take the antiderivative, you're adding 1. So that's like adding 2 over 2. So that'd be the u to the 3/2. Divided by 3/2 is multiplying by 2/3. So 2/3, 4 minus 2x to the 3/2 plus c. Okay. So this is going to show you where it doesn't cancel out perfectly. And all of those, they happen to cancel out perfectly, which was super nice. This one doesn't have that du sitting out front. So you still do it the same way. U is 4x minus 9. Du in this case is just 4 dx. Solve for dx. So now I don't have something sitting in front. So this is just u to the 7th, and dx is du over 4. Now we can just pull out that. This is technically a 1/4, okay? It's in the denominator. So this 1/4, we can just pull it out front and not really worry about it. It's just going to get multiplied times the answer. So we're going to have 1/4 u to the 8th over 8 plus c. These are multiplied, so top times top, bottom times bottom. So u to the 8th over 32 plus c. So 4x minus 9 to the 8th over 32 plus c. Same idea here. Remember, if it's a trig function, it's usually the argument of the trig function, which would be this, x to the 1/2. If that's your u, your du is 1/2 x to the negative 1/2. Or 1 over 2 square roots of x. And again, if we solve for dx, in this case, if I isolate dx, I'll be multiplying by 2 root x. Okay, so I'm going to substitute in here. I have cosine, and instead of writing, hold on just a second. Sorry about that. Let's go back. I have a call. Okay, so let's see. Go back to what I wrote down. U is the square root of x, which is x to the 1/2. Du is 1/2 x to the negative 1/2, which is 1/2 root x. And so if you solve for dx, if I solve for dx, you multiply by 2 root x. So I'm going to substitute this in for dx. Okay, so I have cosine. Instead of the square root of x, I'm going to write u. And then instead of dx, I'm going to write 2 square roots of x dx. And then I still have divide by the square root of x. So what happens is these square roots of x cancel. It should always work out where the variable x goes away. If it doesn't, oh, whoops, I wrote dx to du. If it doesn't, then you did something wrong, or you need to do something else, or it's not going to work. And you have this 2 left over because it was double the derivative, so this 2 can come out. You can have scalar multiples left, like a number, like 2 or 5/7 or something like that. You cannot have x's left over. Now, the antiderivative of cosine is sine. The 2 just hangs around, and then at last you plug back in what u was, which is the root of x. So this is your answer. Okay. This one, when you have a trig function, sometimes it can be tricky, especially when secant squared is involved. But general things to keep in mind is you pick the thing inside the parentheses. This cosine to the 5th x really means this. So I'm going to pick cosine because it's the thing inside the parentheses. But if it's not, you can also think about which thing is the derivative of the other one. And that kind of in a back way helps you figure out what u is. So u is going to be cosine of x here, which means your du is the derivative of cosine, which is actually negative sine x dx. Solve for dx, that means you divide by negative sine. And so I have sine x, and then I have u to the 5th, and then instead of writing dx, I write this, du divided by negative sine x. So the sine x's cancel, but you're going to be left with this negative 1. So this is going to be negative u to the 6th over 6 plus c. So negative cosine 6x over 6 plus c. You can write it like that, or you can write it like this, where you put in parentheses raised to the 6th. Now this one, you might be thinking, which one do I pick? Because they're both kind of like, quote unquote, on the inside. Secant squared could be like secant squared. But here's the thing, secant squared is special. Secant squared is the derivative of tangent. So I know that this is going to be my u because this is the du. So u is tangent because I know, whoops, I wrote u, because I know the derivative is secant squared. And at this point, like you don't have to always solve for dx. I just have done that to make it simple, but just to kind of show you, some teachers show that this guy, you make it equal. So you make it equal to the du. So I see that that is just literally du. So I can write down, u to the 1/3, and then instead of writing secant squared, I can write du. So we're going to add 1, so that's like adding 3 over 3. So u to the 4/3, and then that'd be a 3/4 in front. Let's use the 3/4, and then tangent x to the 4/3 plus c. Okay, let's do this one. When you have an e involved, usually what the thing that is being raised in the exponents, that is your u. So your u is x squared plus 2x. Your derivative of that is 2x plus 2. Now notice this doesn't look just like that, but you can kind of make it look like that because I notice I have a 2 that is a common factor. So you can pull out that common factor, and then I'll show you the solving for dx way just to be consistent. If I solve for dx, and then I go to substitute these things in, I'll have, instead of writing x plus 1, I will have, oh no, I do need to write x plus 1 still. And then that's e to the u. And then instead of writing dx, I'm going to write du over 2 times x plus 1. These cancel. And so I have 1/2 e to the u du. And the integral of e to the u is actually just e to the u. So 1/2 e to the x squared plus 2x plus c. This one, I see something raised to a power. And so we're going to try that as our u. And sometimes I will just say, sometimes in calculus, you have to just try one way when it comes to U substitution and see if it works. The derivative of this is e to the x minus e to the negative x, because the derivative of e to the u is e to the u du. So when you multiply by the derivative of this, you get -1. Divided by e to the x minus e to the negative x. So that means I'm going to have this 2 that. I'm going to go ahead and pull out the 2 so you can see it. 2 e to the x minus e to the negative x over u squared. And instead of writing dx, I write du divided by e to the x minus e to the negative x. And I see that these cancel. So you're left with 2 over u squared, or 2u to the -2. When you take the antiderivative, you add 1 to the power, so 2u to the -1 divided by it. So that's going to be -2 over u, and u is e to the x plus e to the negative x plus c. So that's how you do one like that. Sometimes you have this situation where the du doesn't cancel. Okay, this is double linear. I always just call it kind of back substitution. And the way you can kind of recognize it is that the power on x is 1. So when I go to write out what u is, the power on x is 1 here and here. I get x plus 5, and then if I take the derivative of that, I get 1. And then I realize, oh no, this isn't going to work well. So anytime this happens, you need to write down 3 things. 3 things. U, du, and solve this for x. So rearrange this equation and solve for x. Well, that just means you subtract 5. So it'd be u minus 5. Now you're going to substitute in for all 3 of these pieces. Instead of writing x, I write u minus 5 in parentheses. Instead of writing x plus 5, I write u. And then instead of writing dx, I write du because they're equal to one another. So you basically changed which one has the power. Now the single variable has the power, which means you can easily distribute that in. U to the 7th minus, u to the 8th, you got to add the exponents, minus 5u to the 7th. Then you're going to take the antiderivative by adding 1, dividing by it. Well, I need to add 1 accidentally. 5u to the 8th over 8 plus c. So u to the 9th is x plus 5 to the 9th over 9 minus 5x plus 5 to the 8th over 8 plus c. Okay, this one, I'm going to make the u in the thing inside the square root. Your du is 1 dx, and then substitute back for x equals u minus 4. So this is going to be a little complicated because you're going to plug in for x. So I'm plugging in u minus 4 for that x. So 2 times u minus 4 plus 1 over the square root of u, and then du. Now I need to distribute, so that'd be 2u minus 8 plus 1 over the square root of u. And so that would be 2u minus 7, and you can put them both over u to the 1/2 or the square root of u. And then I'm going to simplify this by subtracting the exponent. So this is like 2u to the negative 1/2 minus, positive 1/2. 7u to the negative 1/2. And then you can take the antiderivative by adding 1. So 2u add 1, so add 2 over 2, so it'd be 3/2 times the 2/3 minus 7u add 2 over 2, so that would be to the 1/2, and then multiplied by 2 plus c. So if I write up here, since I ran out of room down there, I get 4/3. U is x plus 4 to the 3/2 minus 14 x plus 4 to the 1/2 plus c. Okay. So this one is a little tricky too. So since secant is odd and not even, what you can do is you can save out one secant to be the derivative, because the derivative of secant is secant tangent. So I can write this as secant 7x to the 4th, and then I have secant 7x tangent 7x dx. And I know this will work because if my u is secant of 7x, my derivative would be secant of 7x times tangent of 7x times 7 because of the chain rule. So if I solve for dx, you will have this, 7. You're going to have 7 secant 7x tangent 7x. So if I go to substitute, this would be u to the 4th, secant 7x, tangent 7x, and then dx is du divided by 7, secant 7x, tangent 7x. So this cancels with that, and you're left with this 1/7. 1/7 u to the 4th, and so 1/7 u to the 5th over 5, and so that is 1 over 35. U is secant, so plug back in your secant to the 5th plus c. And if you try to take the derivative of this, 7x, you could check and it would be this. Because if I brought down the 5, it would be 5 over 35 secant to the 4th 7x times the derivative, which would have been then secant 7x tangent 7x times 7. And so that 7 times 5 would cancel with this 35, and you would have this, would give you that secant to the 5th. Okay, and then if there's bounds, there's a couple ways of thinking about it. So one way is you write out U substitution. So U is 4 plus x squared. Du is 2x dx. Solve for dx. So this would be 5x over u squared. Dx is du divided by 2x. So the x's cancel, which that's the important part. So I'm left with what on top? Now see, I'm left with this 5 and a 2, so I can just pull out 5/2 and write that as u to the negative 2. So 5/2 u to the add 1. Oh, I don't need u plus c. So this would be negative 5 over 2u. And then you can plug back in what u is. U is 4 plus x squared. And then I can plug in my bounds. So notice I didn't do anything with these bounds until I plugged back in terms of x, and I kept the bounds the same. So it'd be negative 5 over 2 times 4 plus 1 squared minus a negative 5, which would be plus 5 over 2 times 4 plus 0 squared. So negative 5 over 2 times 5. So these 5s will cancel, plus 5 over 2 times 4, so 8. And so you would add that together, 5/8 minus 5/2, and that would be your answer. So I want to show you another way of thinking about it, is you can change the bounds as well. So we have the same u and the same du. So I have 5x and I have the u squared, and dx is du divided by 2x. So then it's 5/2 u to the -2 du. You can change the bounds if you want. So these are understood to be x equals because these are the x variables. So x equals 1. Well, if I plug it over here, then that means that u would be 4 plus 1 squared, so 5. And if x is 0, then u would be 4 plus 0 squared, which would be 4. So I can do this. I can say I'm not going to rewrite it back to terms of x's. I'm going to take the antiderivative. That'd be u the -1 over -1. So that'd be -5/2 from 4 to 5. So -5 over 5 minus the negative. So plus 5 over, whoops, I lost my u. There you go. I lost my u. Over 5 times, 2 times 5 here, 2 times 5, and then 2 times 4. So again, the -1/2 plus 5/8. So those are just two ways of doing the same problem. Okay, last ones, if I do u equals 1 minus x squared, du equals -2x dx. So I get x, the square root of u, and then instead of writing dx, I write du over -2x. So these cancel. -1/2, u to the 1/2. So add 1, that would be 3/2 times 2/3 times the -1/2. These twos can cancel. And so this is -1/3, 1 minus x squared to the 3/2 from -1 to 0. And then you would plug in 0 first minus the negative. So positive 1/3, 1 minus -1 squared to the 3/2. -1 squared is 1. So this would 0 out. So you just get -1/3 for this one. And this one, your u is the exponent, -x squared over 2. So your du would be -x. So this is x, e to the u, and then instead of dx, we're at du over -x. So it's just going to be negative e to the u from, oh wait, then let's plug back in, negative e to the -x squared over 2 from 0 to √2. So negative e to the -√2 squared over 2 minus negative e to the 0, which is 1. Negative, or square root of 2 squared, that's just 2. 2 over 2 is 1. So negative e to the -1 plus 1. So 1 minus 1 over e. Okay, I did want to say that I have a whole other video from when I taught calculus several years ago. I'm going to pull up a whiteboard for a second, where I talk about using pattern recognition, and I will share that video as well. I'll put it underneath this one. And so what I mean by pattern recognition is if you have something like 4 and then the 4x plus 1 to the 5th dx, you can kind of understand that the chain rule had been done. Because if you remember when we had the chain rule, if we had something like this, we would pull the 6 down, decrease this by 1, multiply by the derivative of the inside. We're going to do the exact opposite of that. So if you notice that there's an inside, you look in here and you take the derivative of the inside and you divide by the derivative. So this goes away. Then you increase the power by 1 and divide by the new power. And you're done. It works as long as the variables cancel out. So I notice this guy has 1 bigger power, right? I look in here, I take the derivative of x squared, which is 2x. I divide by the derivative, then I increase this by 1. So 1/2 x squared plus 5 to the 11th, divide by 11. So 1 over 22 x squared plus 5 to the 11th plus c. It works for all trig. Well, I should say most trig. So if I'm integrating and I have like cosine of 2x. I know the answer is sine of 2x, but then instead of multiplying by 2, you need to divide by 2. So if I had sine of 5x, it would be negative 1/5 cosine of 5x, because you need to divide by the derivative. Since when you take the derivative, you multiply by the derivative. When you're going backwards, you need to divide. So say I had something like this, secant squared x squared. Secant squared, I know, goes to tangent. I just have to figure out the coefficient. And the way you figure out the coefficient is you look in here and you divide by the derivative of this. The derivative of x squared is 2x. As long as the variables cancel, you know that this shortcut works. And so what's left in front here is 1/2. So this is called pattern recognition, and I will have a whole video where I can demo this, and you're welcome to look at that as well. Do whichever method makes most sense to you. I just kind of wanted to mention that. And as always, please reach out if you have questions. Thank you.